Have you ever wondered what makes things go? That's energy. Energy is basically the fuel for everything that happens, whether it's a car driving, a ball rolling, or even you thinking right now. When you kick a soccer ball, the energy from your foot doesn't just disappear. It transfers into the ball, making it zoom across the field. This idea of energy moving from one place or object to another is called energy transfer. It's the starting point for understanding how the whole universe works. One type of energy we see all the time is kinetic energy. The word kinetic just means motion. So, kinetic energy is the energy of anything that is moving. Think about a tiny pebble rolling slowly. It has a little kinetic energy. Now, imagine a huge truck speeding down the highway. It has a ton of kinetic energy. We know that if we want to change an object's motion, like making it go faster or stop, we have to transfer energy. This slide summarizes a really important science idea. Whenever an object's motion or kinetic energy changes, that means energy is moving either to it or from it. If you throw a baseball, you transfer energy to the ball to get it moving. When it hits the catcher's mitt and stops, the energy is transferred from the ball. It doesn't just vanish. It gets transferred into things like the heat in the glove and the sound of the thwack. The most important rule about energy is the law of conservation of energy. It's a huge concept, but it boils down to this. You can't create energy out of nothing, and you can't destroy it. It only changes its form or moves to a different place or object. We imagine a system, like the baseball game example, and as long as that system is closed, the total amount of energy stays exactly the same. It's like having a set amount of Legos. You can build different things with them, but you still have the same number of blocks. Energy is like a superhero with many different disguises. We give these disguises special names, like kinetic for movement and potential for stored energy, like a spring that's been compressed. There's also thermal energy, which is just heat, sound energy from vibrations, and the energy in things like light and electricity. When energy transfers, it often transforms at the same time, switching from one form to another. Like a roller coaster turning potential energy at the top of the hill into kinetic energy as it rushes down. Let's use a fast car as an example of energy transformation. The car starts with chemical energy stored in the gasoline. The car's engine is designed to turn that chemical energy into kinetic energy, or motion, which is the useful thing we want. But hold on, the engine also gets really hot, right? That's thermal energy. And the car is loud. That's sound energy. The car didn't want to make heat and noise, but those forms of energy transferred out anyway. The idea of energy being transferred out or lost brings us to the concept of efficiency. Efficiency is all about getting the most out of what you put in. In an energy system, it's the ratio of the energy you actually want, the useful output, compared to the total energy you started with, the input. When a machine is highly efficient, it means it doesn't waste much energy on things like heat or sound. Most of it goes into the intended job. If you've ever pushed a heavy box across a floor, you know about friction. Friction is the force that acts against motion when two surfaces rub together. It's the number one reason energy transfers out of the useful path and turns into thermal energy or heat. Think about rubbing your hands together really fast. They get warm, right? That's kinetic energy turning into thermal energy due to friction. It's unavoidable, and it lowers the efficiency of every real-world machine. As sixth-grade scientists, we need to be able to collect and analyze data to track these energy transfers. Since we can't actually see energy, we look for empirical evidence, observable changes. The most common evidence for energy transfer is a change in motion, like speed or height, or a change in temperature. By carefully measuring these things, we can make an argument about where the energy went, even if we can't calculate the exact amount. Let's investigate energy transfer with a simple, fun experiment: a bouncing ball. Imagine dropping a ball from a certain height. At the top, it has maximum gravitational potential energy, stored energy. The system includes the ball, the air, and the ground. The useful purpose of the bounce is for the ball to go back up. We'll measure the drop height and the rebound height, and the difference will tell us about the energy that was transferred out of the system. When you drop a ball, you'll notice that it never bounces back up to the exact same height you dropped it from. It always falls short. That's the key piece of evidence. If energy were 100% efficient, it would go back up to the same height because all the potential energy would turn into kinetic energy, and then back into potential energy. But since the rebound height is lower, we know that some of the energy had to be transferred out of the ball and the rebound system. So where did that missing kinetic energy go when the ball hit the ground? It didn't disappear. It transformed into other forms of energy that transferred away. For one, you heard it, right? That's sound energy. Also, the ball and the spot on the floor where it landed got slightly warmer. That's thermal energy caused by the impact and the tiny bits of friction. Those forms of energy transferred out to the environment, making the overall bounce less efficient. Engineers and scientists often use flowcharts or Sankey diagrams to make tracking energy easy to visualize. You start with one big arrow representing your total energy input. Then you draw lines to show where the energy goes. A wide straight arrow shows the useful energy output, what you wanted. Any other arrows splitting off, like those for heat and sound, are the transferred out energy that lowers the efficiency. It helps us see exactly how much of the energy is actually doing the job. A classic example of efficiency is the light bulb. Think about an old traditional light bulb you might have seen. You plug it in and it gets really bright. That's good. But if you touch it, it's also extremely hot. The whole goal of a light bulb is to produce light, useful energy. The heat it produces is energy that was transferred out, or what we often call waste energy. The amount of heat an appliance makes is a huge clue about its efficiency. Comparing the old incandescent bulb to a new LED bulb gives us a clear picture of high versus low efficiency. The old bulb uses up most of the electrical energy to make heat, nearly 90%. Only about 10% actually becomes light. That's very low efficiency. An LED, on the other hand, converts about 85% of the electrical energy into light and only 15% into heat. That massive difference is why switching to LEDs saves so much energy. They are just vastly more efficient. This concept of comparing useful output to total input connects perfectly to what you're learning in math. We can use a ratio to express efficiency. If a machine uses 100 units of energy and produces 85 units of useful work, the ratio of useful energy to total energy is 85 to 100. This simple comparison is all you need to track how well a system is performing. The higher the useful number compared to the total, the more efficient the system is. The whole point of understanding energy transfer and efficiency is to help engineers design better things. If they know that friction is causing a lot of energy to transfer out as heat, they will try to reduce it. They use lubrication, like oil, to make moving parts glide smoothly, or they use materials with low resistance. When you design a device, you are constantly trying to find ways to maximize the desired output and minimize the transferred out energy. Think about what happens when you try to keep a cold drink cold on a hot day. You use a cooler, right? The cooler uses insulation, material that is designed to slow down the transfer of thermal energy. An experiment could be simple. Pour hot water into a regular cup and an insulated cup. If you measure the temperature change over 10 minutes, the water in the insulated cup will be hotter. That's empirical evidence that the insulation is successfully reducing the transfer of thermal energy out to the surroundings. It's important to accept that in our everyday world, 100% efficiency is impossible. Everything you do, from riding a bike to charging your phone, involves some energy transforming into a form we don't want, which usually ends up as heat. It might be tiny, but some energy is always transferred out of the desired path. This constant loss is why we keep needing to put new energy into a system to keep it going. Let's wrap up our deep dive into energy transfer efficiency. Remember, energy is conserved. It just changes form or moves. When the motion, kinetic energy, of an object changes, energy is absolutely being transferred to or from it. We use the concept of efficiency to track how much of that transfer is useful. Finally, always look for the evidence of transferred out energy, like heat and sound, because they tell the story of a system's efficiency.